This is part 2 of section 1.3, linear combinations and span. We'll begin with a definition. V1 to Vp are vectors in Rn, and C1 to Cp are scalars, real numbers. We consider this combination C1 V1 plus C2 V2 and up to Cp Vp, scalar multiple and vector additions. Then it is called the linear combination of V1 to Vp with weights C1 to Cp. That means that the weight sum of vectors is called the linear combination of the vectors. That is the definition. Let's see this example. V1, V2 in R2 is given as in the figure. The collection of all linear combinations of V1, V2 must be the same as R2. That means that if you choose any vector in R2 or identify it as a point, then now you can reach at this point by using V1, V2 as a combination of these two vectors. Okay, we can do that, right? For example, at this point, here we expand line through along with V1 direction, and now in parallel direction of V2 from here, we can reach over there that way. So that a multiple of V1 and a scalar multiple of V2 and added, then we can reach at that point. So that this position vector in R2 can be expressed as a linear combination of V1 and V2. For any other point, you can do it. So that means that the collection of all linear combinations of V1, V2 must be the same as R2. Okay? A vector equation is of the form here for vectors A1 to AP. Left-hand side is their linear combination and equals a vector right-hand side. So once equation is given in this way, we call it a vector equation. Of course, over there, x1 to xp are weights. Okay. Let's see this example. A1, A2, A3 are given in this way, and B is given in here. And determine whether or not B can be generated as linear combination of A1, A2, A3. That means that here we should determine whether weights x1, x2, x3 exist such that the linear combination of these three vectors become the right side B. That here that equation can be written in this form. Early in Remark 1.25, we saw one example that linear combination of vectors can be written as metric vector multiplication. So for this, the algebraic system, we have to check if the solution exists. So now if B is generated as a linear combination of A1, A2, A3, then equivalently here, this linear system has a solution, right? Now, how can we check the existence of solution? We may start with augmented metric, and then once it is consistent, then here we can say that B can be generated as a linear combination of the vectors, right? Okay, so we start with augmented matrix. Now, A1 is 0, 4, -1. That is the first column of the matrix. And A2, 1, 6, 3, and A3, 5, -1, 8. That is now matrix. And right inside, 0, 2, 8. Okay, not A3. Okay, 0, 2, 3. So this is the augmented matrix. From here, now we have to check if it is consistent. That's all, right? Okay. Yeah, this is now pivot column, and here we can move this one on the top along with -1 multiplied, so that 1, -3, -8, -3, right? And then we write down the second row the same, 4, 6, -1 and 2, and that is now 0, 1, 5, 0. Okay. Now here, this is a pivot, and we have to eliminate the below of the pivot. So here we try to eliminate the 4. Okay, 1, -3, -8, -3 is the same. Okay, and then 4 times subtraction will make a 0. 4 times subtraction will make 18. There is -12 is negative is 12, so that 18. 4 times subtraction, so 32 is added, so that 31. Now 4 times subtraction, that is now so that 12 is added, so it's 14. Now that is here 0, 1, 5, 0. Okay. Now here, from this one, 1, -3, -8, and -3. And then, okay, this is 1, so that we may interchange these two rows. And we try to subtract 18 times for that row, then it'll make, we can make a 0, so that 1, 0, 1, 5, 0, and then 18 times subtraction, 0, 0, 18 times subtraction, that is -90, so that, okay, that is -59, and here, okay, the same is 14. So this is pivot, and pivot leading edge tree, that is again pivot. So we have a third pivot, and in each row we have now pivot, and in the matrix A, so that this one has a solution. In fact, this one has a unique solution. Once you finish the computation, then you'll find x1, x3 uniquely. But anyway, we have solution because here we have here now that pivot here. Okay. Okay. So the answer for this one is yes. We can B can be generated as a linear combination of these 3 vectors. Okay. The vector equation x1, a1, x2, a2, and here plus xp, ap equal b has the same solution set as a linear system whose augmented matrix is now a1 to ap and b. we did already in this example. Right? B can be generated as a linear combination of A1, A2, AP if and only if the linear system AX equal B, whose augmented matrix is consistent. Right? Okay. Here we have definition. V1 to Vp are P vectors in Rn. Then span of these vectors is the collection of all linear combinations of V1 to Vp. That can be written in the form, each entry in this span can be written in this form, where C1 to Cp are weights. That means that span of phi vectors can be written in this way, collection of all vectors, and each one has this form for some C1 to Cp weights. Right? Here, look at this figure. Now, we consider one vector, and V, the V is here. Now, if we consider the span of V, then that is collection of CV, basically. C is a scalar. So all possible C can be considered. So that once a C is less than 1, then here the vectors will be around there. And if it's larger than 1, then go over there. Once C is negative, then go the other direction, so that eventually span of V is line, including this vector V. Now here for, okay, that must be V here. Okay, for this one, we consider span of U and V. If U and V has different direction, then by using linear combination, we can fill this plane. So any point on this plane can be made by using a linear combination of U and V. So that means that the span of two vectors directing different direction will make a plane. As a whole plane, including U and V, is the span. Okay. Okay. Determine if B is a linear combination of the columns of the matrix. That means that determine if B is in the span of columns of the matrix. Okay. So once B is a linear combination of the columns of matrix, then here if we say this is A, then AX equal B has a solution, so that we have weights such that the columns of a matrix and linear combination of them will be that one, so that this linear system should have a solution. Now we have to check that, and in order to check it, now again we start with the augmented matrix. The problem is quite similar as in this one, right? Okay. In fact, that is the same problem here. So we may check the possibility by starting with augmented matrix. Okay. Okay, let's do it. The augmented matrix is here now. A is 1, 0, 5. There is a -2, 1, -6. There is 0, 2, 8. And right side is and 2, -1, 6. Okay, 2, -1, and 6. Okay, from this one, now first one, 1052 is not changing, and twice added. So always once we start with a pivot, then below pivot must be empty. So twice is added, then it's 0. Twice added, twice added, and twice added. So that is a 3. And that one is now divided by 2. We have here 1, 4, 3. Okay. Here now that is this pivot, and this becomes another pivot, and below the pivot here we have to eliminate. Now the roots are the same, so that just simple subtraction makes this row 0. Okay, so 0, no, that is 1. Okay, 1, 0, 5, 2, and 0, 1, 4, 3, and 0, 0, 0, 0. Okay, this is pivot and leading one, and then except leading one, everything else is 0. Okay, so it is infinitely many solutions, because here these are basic variables, x1, x2, and x3 is a free variable. So existence of a free variable makes infinitely many solutions. Right? Okay, let's try to finish finding x1, x2, x3. Okay, from that reduced echelon form, here now x1 equals same as, okay, right hand side 2, and there's a minus 5 x3, and it is moved to the right side, and x2 equals same as now 3 minus 4 x3, and x3 is a free variable, so we can say x3 is x3. Now from this one, the vector x is same as a constant vector 2, 3, 0, and then minus x3, and the direction is minus, okay, that's plus, and minus 5, and minus 4, and here this is 1, right? So for arbitrary choice of x3, it'll be a solution, so that B can be generated as a linear combination of here the columns of A and infinitely many ways. Here x can be chosen by choosing x3 arbitrarily. Okay. Find h so that 2 on h lies in the plane spanned by a1, a2. That means that, again, here metric a1, a2. So we have to find h such that now a1, a2, this metric, times x becomes here that one, 2, 1, h. Okay, so we have to find h so that is in the plane spanned by that, which means that the plane spanned by a1, a2 is a linear combination, just a collection of linear combinations, so that here we have to find h such that this system has a solution. Okay. Now, to figure out h, again the same way, we start with augmented metric. A1 is 1, 2, 3. A2 is 2, minus 1, 1. Now, right side, B is 2, 1, H. Okay, from this one, now this is the non-zero column. Okay, there is a pivot, and we have to empty below the pivot. So here there is 1, 2, 2, twice subtracted, that is 0, twice subtracted, minus 5, twice subtracted, and that is minus 3. And then that is 3 times subtracted is 0, 3 times subtracted, then now that is a minus 5, right? 6 is subtracted, okay. And then that is now here h minus 6, right? Okay. In order to have solution now here, okay, once we try to eliminate that one, then, okay, let's try to eliminate it from here. Then 1, 2, 2, and now that is 0. Let's try to multiply minus 1, so 5, and now 3, and then subtract then 0, now 0, subtraction, so that plus 3 is applied, so h minus 3, right? In order for this system have a solution, this must be 0, right? If it is non-zero, then 0 is non-zero, so it is impossible. So that it must be 0. That means that h must be 3. That's the answer for the problem. Okay. Here we summarize what we have done. A vector is in span of v1 to vp, the vectors. That is equivalent to say that here x1, v1, so the linear combination of the vectors equal b has a solution. And also the same way we can say that the augmented matrix has a solution, right? Okay, that's a summary we have learned through this second part of the section. Okay, now we have true or false problem. Another notation for the vector 1 minus 2 is 1 minus 2. So that means that here is the same. Here, this vector and this one are the same. Is it true? It's not true. And this is a column vector, but the shape of this one and that one are different, so that they are not the same. So it is false. The set span UV, span of U and V is always visualized as a plane through the origin. Is it true? If U and V have different directions and non-zero, then it will make a plane. However, and one of them can be 0, or U and V can be the same, then it can make a line. And if U and V are 0, then span of 0 vectors will be 0, so that it can be a point at the origin, and so that eventually the span of U and V can be a point, can be a line, can be a plane. Not always a plane, so it is false. When U and V are non-zero vectors, the span of U and V contains the line through U and the origin. Is it true? It must be true. And U and V are non-zero vectors, then span U and V should at least contain at least the line through U and the origin. V can be quite different from U, then it can be a plane. However, here span should contain at least a line through U and the origin. It should contain U at least. So the statement is true. Okay? Okay. That's the end of the section. Thank you.